once you learned how to take a derivative in Calculus 1, one of the next things you did was say, well, I can take a derivative and I get a function. Can I take a derivative of a derivative? And of course the answer is yes. And what you get is the second derivative, right? Well, as you might guess now, we have two first derivatives. So talking about a function of two variables anyway, we have df dx and df dy. Well, what if so how many second derivatives could we have? Well, we can do x then y, we can do x then x again, we can do y then x, and then we can do y then y again. So we have 4 possible second derivatives for a function of two variables, right? So let's kind of write down the notation for this because it can get a little tricky, right? So let's just stick with having f be a function of two variables, just to keep the notation simple. Of course, you can do this for functions of 3 variables and 4 and as many as you want. But let's just stick with 2 variables for now. Okay, so you already know about df dx and df dy. Right? One way I want to get you to think about what df dx looks like, and you might remember this from Calc 1 as well, we're taking this thing called d dx and we're applying it to the function f. And that gives us df dx. Okay? So there's a point to this, trust me. So what about when we start doing second derivatives now? Well, so let's say I want to take df dx and do another derivative with respect to x. Well, you might remember from Calc 1 you had d squared f dx squared, and it's going to look the same here. So the second derivative, you could have d squared f dx squared, right? Which is, another way we write this is f sub xx, right? But what I want to get you used to is thinking this is d dx of df dx. And here's the reason I want you to think about it like this. Because these guys are coming in from the left-hand side. So when we read this, we read it as do the x derivative, then do it again. Here we kind of have to read backwards. Now where that's more evident is, let's say we want to do the derivative of f. I'm going to do it a little bit backwards here now. First with respect to x, then with respect to y. Okay? So let's say I want to find this derivative. So remember, this one's first. This one is second. Okay? So what that means is first I do df dx, and then I am doing d dy to that. So when I write this down, I still get d squared f on the top, but the bottom, dy and dx are different, so we can't just do this sort of dx squared, or we can't write like dxy. What we have to write, we have to keep the order here, dy dx. Okay? So you see these look sort of back to front from each other, right? And again, it's based on how you think about these things working. Here we're just listing the order we're doing the derivatives in. Here we're thinking the derivative is what's called an operator. And these guys hit a function from the left side, so they kind of stack outward. Right? So that's why they look backwards to each other here. Right? But that's just a notational thing to get used to. So let's do an example to kind of just find all 4 of the second partial derivatives. Right? So we're going to say find all second partials of, marker's running out again. I left my good markers in my office today. My many apologies for that. Find all second derivatives of, what do I want to give you? F of xy. Oh, this marker's so bad. Yeah, x to the fourth, y cubed, minus y to the fourth. So we're going to find all second partial derivatives of that. Right. So we want to find the second partial derivatives of this function here. So to begin with, we have to find the first partial derivatives. Right? So fx is 4x cubed, y cubed. That's it. Right? Y to the fourth is completely gone because it has no x's. Right? And now we do the derivative with respect to y. Well, that one's just 3x to the fourth y squared minus 4y cubed. All right, so we have the two first derivatives. Now we have to take the derivatives of those to get the second derivatives. So let's start by finding the two fxx, fyy. Okay, so another the 3 is just going to come down here, and we're going to get 12x squared y cubed. And over here, for fyy, well, all we're going to get is 6x to the fourth y minus 12y squared. All right, well, that's great. Now let's do the mixed partials. Right? We call them mixed partials because, you know, they mix up the variables that we're taking the derivatives with respect to. So those are fxy is the first one. We have to take the derivative of this guy up here with respect to y this time. And that gives us 12x cubed y squared. And over here, for fyx, we have to take the derivative of this thing up here with respect to x. Right? So that gives us 12x cubed y squared minus 0, because the 4y cubed has no x in it. So, well, that's all the second derivatives. Do you notice anything peculiar about this? So hopefully you notice something very interesting. These two, the mixed partials, they're the same. So you might ask, is that a coincidence or does it always happen? And the answer is, it's not a coincidence. It doesn't necessarily always happen, but it's definitely not a coincidence. And this is something we call Clairaut's theorem, which is Clairaut's theorem. So let's suppose f is defined on a disk D, fxy and fyx are continuous on D. Okay. Then fxy of AB equals fyx of AB. In other words, what that's saying is as long as these two second partial derivatives are continuous on some region, a disk in this case, then it doesn't matter which order we take the partial derivatives in. So what we usually call this, we usually say f is a C2 function on D. That's sort of what we mean here. Right? I guess this is a little more strict than this. What C2 means is all of the second partial derivatives exist, and they're all continuous. Right? In this case, we just need fxy and fyx. But, so, for Calc 3, we're pretty much not really going to give you things that contradict that. So, what that means is, if you do one mixed partial, you can just flip the order of the derivatives and have the answer already. Now that doesn't mean you should go flipping these around. This still means this. If you flip these, it'll be the same. You'll still get the same output, but fxy is strictly in this order when you write it down. It just happens that fxy and fyx are equal. Okay?